Students, now let's take the next topic, which is roles and Lagrange's theorem. We'll start with Rolle's theorem. It is also another important application of the derivative, and the theorem states that if a function f(x) is such that it is continuous in closed interval a to b, differentiable in open interval a to b, and the third point, that the value of the function at x equal to a is equal to the value of function at x equal to b, then there will be at least one value of x, say c, which belongs to a to b, such that f dash c is equal to 0. So if a function is continuous in closed interval a to b and differentiable in the same interval, open interval a to b, and the value of the function at x equal to a and b are same, then there will be at least one root of the function f(x), f dash x in the interval a to b. Let us see what is the geometrical meaning of this theorem. Now suppose we have a function which is continuous. Differential means there is no sharp corner, and continuous means there is no break in the given interval, and the value of the function at a and b are also same. So suppose that this is the function such that it is continuous in the interval, it is differentiable, and the value at x equal to a is same as the value at x equal to b. This is the value of fa as well as fb. So according to the Rolle's theorem, there will exist at least one c for which the slope of tangent is equal to 0. Now if we draw a tangent at x equal to c, then the slope of the tangent will be equal to 0. That is f dash c is equal to 0. We can draw another graph. Now suppose we consider the case of sin x. Let's say this point is 0, this is pi, this is 2 pi. And let's say we consider the interval 0 to 2 pi. Then in this particular case, we know that sin x is continuous and differentiable everywhere, and also f0 and f2 pi both are same, which are equal to 0. So according to the Rolle's theorem, there must exist at least one value of x in this interval 0 to 2 pi such that the slope of tangent is 0. So this is quite obvious from the graph that one such value is pi by 2 and the other value is 3 pi by 2. So there will be at least one value of x in the interval for which the slope of the tangent will be 0. There can be more than one, but at least there will be one if the curve follows the given three conditions. That is, it must be continuous in the closed interval, it must be differentiable in that open interval, and the value of the function at the extreme values of the closed interval must be equal. Now let's take some examples on this theorem. Now we are given some functions along with some intervals, and we have to check whether the Rolle's theorem is applicable on these functions or not. So we start with the first function, fx equal to mod x in minus 1 to 1. So we have to check the continuity differentiability of the function in the given interval and also the value of the function at the extreme points of the interval. Now this question can be solved directly just by drawing the graph of the function mod x in the interval, that is minus 1 to 1. So if you want to draw the graph, then the graph of mod x in the interval minus 1 to 1 will be like this, and we can say that clearly fx is not differentiable at x equal to 0. Therefore, fx is non-differentiable in minus 1 to 1, or we can say that Rolle's theorem is not applicable. So the second point is not satisfied here, so we cannot apply Rolle's theorem to this function in the interval minus 1 to 1. Let's take next example. In the second example, we have the greatest integer of x, and the interval in which we have to check the applicability of Rolle's theorem is -1 to 3 close interval. So the function here, if we consider the function greatest integer function, we already know that the greatest integer function is discontinuous at the integer points. So it is not satisfying the first step itself. Hence, Rolle's theorem is not applicable. So since greatest integer x is discontinuous at integers, and though it may be continuous at -1 and 3, for that we will have to see the right hand limit and the value of f -1 for x equal to -1, and for x equal to 3 we will have to check left hand limit and f3, but at 0, 1 and 2 it's going to be clearly discontinuous. So therefore Rolle's theorem is not applicable for this function. We can draw the graph also, which will be a better method to understand and will be easier for you. So we draw the graph of the greatest integer function of x in -1 to 3. So let's say this is -1, this is 0, 1, 2 and 3. So first let us draw the graph from -1 to 0. It will be like this. There will be break at 0, then for -1 to 0 we will have the value, for -1 to 0 the value of the function will be -1. For 0 to 1 the value of the function will be 0. For 1 to 2 and finally for 2 to 3 the value will be 2, and for x equal to 3 the value will be 3. So clearly we can see that the function is discontinuous at x equal to 0. RHL is -1 while LHL is RHL is 0 while LHL is -1. At x equal to 1 LHL is 0, RHL is 1. At x equal to 2 LHL is 1, RHL is 2, and at 3 also it is discontinuous because f3 is 3 while f of -3 minus, that is the left hand limit, is 2. So clearly the function is discontinuous, hence Rolle's theorem is not applicable. Let's take another example. we are given a cubic polynomial and it is defined on the interval 1 to 3 and satisfies the Rolle's theorem. For C equals 2 plus 1 by root 3, then find the values of A and B. So since it is a cubic polynomial, so obviously it is continuous and differentiable in the given interval. Now it is also given that it satisfies Rolle's theorem for C. C is the value which lies between 1 to 3. That means for this value of C, the derivative will become equal to 0. And also since the given polynomial satisfies the Rolle's theorem, so also fa must be equal to fb, and a is 1 and b is 3. So fx is this polynomial and it satisfies Rolle's theorem. So therefore f1 must be equal to f3. The value of f1 will be, put x equal to 1, is equal to f3. So this is 27, 3, this is 54 plus b. This gets cancelled. This is a minus 5, while this is 3a minus 27, or this is 27 minus 5, while this is 3a minus a. So the value of a is 11. So with the help of the third condition of Rolle's theorem, we get the value of a now, even though we are given the value of C, but if you calculate f dash x, then f dash x is 3x square minus 12x plus a. So even if we put the value of C which is 2 plus 1 by root 3, we will be getting the value of a again. We are not going to get the value of b. Both the results are independent of b. So the equation is holding for a is equal to 11 irrespective of the value of b. So b can be any real number. If you will put c here, this equal to 0, you will put x, you will again get a is equal to 11. So we can say that for a is equal to 11 and b belongs to any real number, Rolle's theorem will be applicable for this function in the interval 1 to 3, and for that we will get the value of c as 2 plus 1 by root 3.